Now we want to talk about more about causation. So we have a causal structure. Our goal is to discover different causes of some outcomes. For example, we want to discover some hidden factor that has an effect on both smoking and lung cancer. This is a more complex example that we see in biology. But before I begin, I should explain some elementary definitions which are really important. For example, in econometrics, they talk about instrumental variable, Z. So, but here in causal theory of Judet-Pearl, we talk about we do some adjustment for Z, and in econometrics they call it instrument variable. So we have another variable, treatment variable, outcome variable, and confounded variable. The difference between confound and extraneous variable is that confound variable has an effect on both outcome and the intervention, but extraneous variable is just a single relationship. So the spread in your regression for pair trading is like a noise. Forex doesn't tell you what the cause of. For example, I just, in order to understand, to discover these causal structures in Forex market, I always review and try to discover the relationship between different spreads. For example, Euro USD, GBP USD, and this spread. What is the relationship between this spread and another spread? It could be GBP USD, Euro USD. So Judet-Pearl defines some definitions such as latent structure and minimality, which is very important, and consistency. For example, A and B are minimal because they are satisfied independence rules, and nothing more, because it is the minimal requirement. So it is a minimal, like minimal art. Stable distributions, it's just like robustness in system theory, in control theory, in dynamical system theory, if you are familiar with. So we just change a parameter, adjust a perturbation of parameter, and see if the system view, if the system is very sensitive to that change in structure, and it is very bad if it is dependent on such a variable. So we call the system is not robust. And here in causality theory, we talk about stable distribution, some faithful structures that Judet-Pearl talks about. So if alpha has a relationship with the gamma, then and something big happens in the structure, the probability distribution changes very rapidly, then we say that it is not a stable distribution. We have inductive causation. Of course, there are tens of algorithms, such as PC algorithm, that's very famous. But I say that none of them are perfect. They are still in their infancy, and because they're just random search, I don't see any intelligence in that. And he defined potential cause. The potential cause means that it is there are other contributors and the outcome, not just X. X is just one of the contributors. He defined genuine cause. He defines spurious association, and I want to talk about interventions because right now we talk about raw data. Now we talk about interventions. So what happens when we just fix some variable, let's say x, and see the effect of that if we didn't change and if we changed that? So it is equivalent to the structure of Rubin that I talked in the past two lectures, and So a causal effect is we want to find if the distribution changes very much when you just fix some variables. And the most important the most important theorem, let's say, is adjustment for direct causes. Because if you have a spurious correlation such as this, as you know, correlation does not imply causation. For example, U.S. spending on science correlates with suicides by hanging, but does not imply that it's a causation. So we just use the tools and techniques of adjusting. We adjust. We should. Why this happens? Because there is a confounding variable that has an effect on both cause and outcome. So if we try to do some investigation to see if there are some causes, there are some adjustments for the cause, then we can get rid of confounding variable. I will talk about it in a second. So we have a pre-intervention distribution and then post-intervention. What happens when we fix some variables? Does it change the distribution quite a lot? Is it so sensitive that it totally distracts the distribution? It becomes something quite different things. For example, let's say, Aristotle has four causes in philosophy. He wants to see if some cause, if it changes the structure or not. And you can formulate it something like this, very beautiful. And so in order to understand the concept of identifiability, I talk about some motivations for that. So the trick is we can break the graph into two pieces, M1 and M2. It makes analysis simpler. You want to infer X from Y, something like hidden Markov model, that you want to infer something from your measurements. You don't know hidden state, you want to infer from that. So the idea of identifiability is finding causality, causal quantity, such that it is become consistent in both pieces. So there are other structures that should be discovered if it is not identifiable. And a backdoor, for example, here there is one backdoor from A to Y, because we can go through this. So V, it is the backdoor. It is blocked by M, because you cannot go. V is not your confounding variable anymore because it is blocked by M. So these confounding variables, such as here, V is a confounding variable. These confounding variables are the source of spurious correlations that I talked about here. Here is a spurious correlation. Why? Just because a variable, a confounding variable here, is affecting both cause and outcome. So we just use a trick and create a variable M. We block it. We call it a collider variable.